So this next recording, we're going to give you a short introduction to enzymes. There's a tremendous amount you can study about enzymes, and when you go on to take biochemistry, you'll learn a lot more of this stuff in much greater detail. So this is just an overview, but it's really, really important to understand. And the enzymes that we're going to look at are primarily protein enzymes. So we want to review then like protein structure and how proteins work to understand really how enzymes can be regulated well. Now, let's talk about the energy components first, and then we'll talk a little bit more about the proteins. So enzymes speed up metabolic reactions by lowering energy barriers. So they're catalysts. They're going to participate in the reaction but not be consumed by the reaction. And in general, enzymes are in most cases proteins, not always, but in most cases proteins. So if we look at the hydrolysis of sucrose to glucose and fructose by the enzyme sucrase, again, oftentimes an enzyme will be named with the ase after its substrate. Now, its substrate in this case is the reactant in this reaction as we break it down into glucose and fructose. Now, this is has a negative delta G, this reaction. So it is spontaneous. But oftentimes the spontaneity, the rate of the reaction, is so slow it's not biologically usable. And so we have to use an enzyme then, a catalyst, to increase the rate to allow this to be functional in our metabolism. Now, what causes that rate to a certain extent is the size of the activation energy barrier. Right, so free energy of activation or activation energy is something you may have heard of before, but this is basically the energy needed to kind of start the chemical reaction. So it's kind of a transient input of energy to kind of get our reactants into a transition state so they can fall downhill to a more stable form and release energy in a spontaneous reaction. All right. So if we look at that in a graph, and this is a classic graph, this idea you have reactants. A and B are covalently bound to each other, C and D are covalently bound, and you can see the free energy on the y-axis is higher for the reactants than it is for the products, so the delta G is less than 0. But you also notice that as you progress through the reactants have to go to a higher energy level before they can fall down to the products, that transition state. And the difference between the starting reactants free energy and the peak of that transition state energy requirement is the activation energy. Right? So that's like a hill, it's a bump of energy we have to get over before we can fall down to the products. Right? So enzymes work by lowering that activation energy. All right? So we're not going to change the amount of energy from the start and end of the reaction. The energy of the system is the same. The delta G doesn't change. But we're going to lower the activation energy. So you can see here comparing the black line to the red line. The reactants and the products are at the same free energy, right? Reactants, regardless of whether you're with enzyme or without, same free energy. Products, with enzyme or without, same free energy. The delta G between the reactants and the products does not change. But if you look at the activation energy without the enzyme compared to the activation energy with the enzyme, you see a striking difference. The enzyme is lower, and that is going to allow the reaction to proceed at a faster rate, right? So when we talk about enzymes, we want to talk about the enzyme substrate. What is the reactant the enzyme is acting on or binding to? That's its substrate. And together then, they form the enzyme substrate complex. Where the enzyme binds to its substrate is called the active site. And oftentimes we talk about what's called an induced fit. Right? An induced fit is going to be a component of how the enzyme is going to catalyze the reaction. All right, we'll talk about this more. So here you can see the substrate and the active site. The active site is going to be very specific for its substrate. But when they're put together, it actually changes the shape of the enzyme. And the enzyme substrate complex then is going to be a different shape, so induced fit. Right? So binding to the active site can lower the activation energy by orienting the substrates in a certain way, straining substrate bonds, providing a favorable microenvironment, and covalently bonding to the substrate. I'm going to leave these details at that level. Again, if you go on more in biochemistry, you can break each of those down and look at very specific examples of how those work. But for now, kind of keep that in your head, and it's going to be okay. Now, again, if we look at that, here are substrates coming in, and some enzyme substrate complex. We've lowered the activation energy. We've converted to products. Products released. Now the enzyme is ready to roll again. Again, we want to remember that the enzyme is in fact catalyst. It participates in the reaction, but is not consumed by the reaction. Right? Now, because enzymes that we're talking about now are all protein-based, things that affect proteins are going to affect the enzymes. Right? So general environmental factors such as temperature and pH, chemicals that can influence enzymes are all going to ultimately affect the shape of that enzyme and how it reacts with its substrate. All right? So each enzyme has an optimal temperature which it can function. And so for organisms with a set body temperature, right, our enzymes have evolved to be very, very efficient at our body temperature. Same with pH, right? So if you look at these graphs, you can see, again, optimal temperature for a typical human enzyme, is going to be around 37 degrees Celsius. That's where the peak of enzymatic activity is seen, where it works best to catalyze the reaction that it catalyzes. Whereas if you're a thermophilic bacteria, a heat-tolerant bacteria, that's going to be much higher, right? Same thing for pH. So for each enzyme, these can be empirically determined. Okay, so you can't just kind of say, oh, there's an enzyme that's going to have a optimal temperature of X, Y, or Z. You have to empirically determine each of these. And some enzymes will have a broader range than others. Now, the other things that can affect enzyme function are what are called cofactors, non-protein enzyme helpers. This is basically your vitamins and minerals. All right? So cofactors can be inorganic or organic. If they're organic, we call them coenzymes. Right? So these are your vitamins. The minerals are your minerals. They're inorganic cofactors that are going to bind to the enzyme to help it work. So this idea of binding to an enzyme and affecting its function is also can also introduce the idea of inhibitors. So you can have competitive inhibitors and non-competitive inhibitors. And competitive inhibitors are going to be a substance that competes with the substrate at the binding site. Non-competitive inhibitors are going to bind to the enzyme, the protein, change its shape such that the protein can no longer bind to its substrate. Right? So if we look at that here, you see normal binding of the enzyme and its substrate. And then competitive inhibition would say you've got this inhibitor here that it gets into the active site, and now the substrate can no longer bind. Non-competitive inhibitor, this is called allosteric binding, which we'll talk about in just a second, binds not at the active site, changes the shape of the protein such that now the substrate is no longer bound. Right? Again, shape, form, and function. This is how proteins work. What are proteins doing? They're doing stuff. In this case, catalyzing reactions. Right? So we need to be able to control enzymes in different metabolic pathways. So again, we can do that by turning genes on or off, as we've seen, or we can affect the protein with a cofactor or an inhibitor to turn it on or off. So let's take a look at this, a couple different ways to control enzymes, and then we'll finish this particular recording. So allosteric regulation is this either inhibition or stimulation of an enzyme when you're binding to the protein not at the active site. Right? So oftentimes these are proteins that are have quaternary structure, are made from multiple polypeptides, right? And we're going to either bind to the complex and stabilize it in an active form, or bind to the complex and stabilize it in an inactive form. Right? So we can see that here is you've got a quaternary structure of a protein complex. An activator is actually going to bind not to an active site. That's allosteric binding, but stabilize this and say you can work well now. You are turned on. Versus the non-functional state, the inhibitor binds it and says you are not functional and you're going to stay that way until I'm not bound. But you can see without the activator or the inhibitor there, you have this vacillation, this oscillation, this equilibrium between functional and non-functional states. And that is how this particular protein was built, such that then activators and inhibitors can be used to control its function. Now, the other way to consider controlling the effect or the activity in an enzyme is cooperativity. And so in this case, what you have is the actual substrate helping to stabilize the structure in the active form. So in this case, again, you've got multiple binding sites, 4 in fact, and the binding of the first substrate then makes it easier to bind the other 3 substrates in the other 3 active sites. So hemoglobin works this way. 1 oxygen is bound which then makes its affinity for subsequent binding of oxygens go up. And that is, again, a classic biochemistry example that you'll cover when you take biochemistry. Now, feedback inhibition is something we've discussed already, but we can look at this now on the level of a protein. Right? So feedback inhibition, the actual product of a metabolic pathway, can actually shut down that pathway at an earlier step. Okay? So now this way we can see now, in this case, isoleucine at the end of this metabolic pathway is actually the cofactor, the inhibitor that is binding allosterically to the first enzyme in the pathway, shutting it down. We've got enough isoleucine. Don't make any more. All right? So you're going to want to review this idea of how enzymes work and enzymes in general, and we're going to go over it again and again and again.